Hello everyone. This is our lecture on section 2.2 on inverse matrices. So, definition. If A is an n by n matrix, this is called a square matrix, then the inverse matrix of A is a matrix A like that, A inverse, such that A times A inverse is A inverse times A is equal to the identity matrix. And remember this matrix, right, that's the matrix with all ones on the diagonal and zeros everywhere else, right? And that matrix, under matrix multiplication, kind of does the same function as the number 1 in the real numbers, because when you multiply any matrix by the identity, right, you get the same thing back. Any matrix by the identity, you get the same thing back. So this A inverse is kind of like 1 over A. So A times 1 over A should be equal to 1 in some sense, which is I in this case. So that's the inverse matrix, if such a matrix exists. It doesn't have to. All right. The easiest case is with 2 by 2 matrices. Okay, so if A is equal to A, B, C, D, and this AD minus BC is not equal to 0, then A inverse, so that's only when this is not equal to 0, A inverse is equal to, well, it's 1 over AD minus BC times DA minus B minus C. Okay, let's check it out. Okay, so A, B, C, D times the scalar 1 over AD minus BC times the matrix D minus B minus C A is equal to, okay, well, let's take that scalar and bring it out front. Okay, you can always just take the scalar and just move it out front. 1 over AD minus BC, A, B, C, D times D minus B minus C, A. Okay, so let's do the product. First row, first column, A times D minus B times C. Oops, I lost my coefficient there, scalar. 1 over, so first row, first column, AD minus BC. First row, second column, minus AB plus AB, 0. Second row, first column, CD minus CD, which is 0. Second row, second column, minus BC plus AD. All right, which is equal to 1, 0, 0, 1, which is I2. All right, so that's what we're looking for. And then you can check the other way. That 1 over AD minus BC times D minus B minus C A times A, B, C, D is I2 as well. Okay, we did it in one direction. You can give it a check in the other direction. Okay, so the 2 by 2 matrix, it has an inverse if and only if that AD minus BC is equal to 0. If and only if 2 by 2 matrix, gotta give it some entries, A, B, C, D, has an inverse if and only if AD minus BC equals 0. Okay? So, more on that later, a generalization of this notion to 3 by 3 and 4 by 4 matrices. That'll come later in the course. But for now, for 2 by 2 matrices, we have that result. Okay. Okay. More generally, when does an inverse matrix exist? It's not in terms of, in a different sense. When do inverse matrices exist? And how do we find them? Okay, well, before we do that, let's talk about elementary matrices first. Okay? First, let's talk about elementary matrices. Okay, an elementary matrix is a matrix obtained from IN by performing one elementary row operation. Okay? So, for example, if I had something like this, 1, 0, 0, 0, and 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0. This is I4 with row 2 switched with row 4. Right? I just switched row 2 and row 4. So that's an elementary matrix. One row operation obtained from the identity matrix. It's a 4 by 4 elementary matrix. Here's another one. 1, 2, 3, 4, 1, 2, 3, 4, 0, 0, minus 1/3, 0, 0, 0, 1. Right, so this is I4, well, I should say it better, obtained from I4 by switching row 2 and row 4. This one is obtained from I4 by doing minus 1/3 row 3. Right, so I took row 3 and I scaled it by minus 1/3. So that's the second type, right? Remember there's 3 elementary row operations: switching rows, multiplying a row by a non-zero scalar, and then adding the most important one, adding a multiple of one row to the other. So this is an example of that. 0, 1, 0, 0, let's say minus 4, 0, 1, 0, 0, 0, 0, 1. Right, so this is obtained from I4 by doing row 3 plus or minus 4 row 1. Right? So that's 3 elementary matrices. Now the cool thing about elementary matrices is when you multiply a matrix on the left by an elementary matrix, it does that row operation to the matrix. So when taking an elementary matrix, E, and multiplying by A by E on the left. So when, I'm not saying this right, given an elementary matrix E and another matrix A, given n, so let's say n by n elementary matrix E and another n by n matrix A, EA is the matrix obtained from A by performing the row operation given by E. Okay, well, I mean, one has to verify this, but let's just check it out, just for example. I mean, we're not going to get into it in too much detail, but let's just check out an example just to see. Let's do 3 by 3. So 1, 0, 0, 0, 1, 0, and now let's do minus 2, 0, 1. Right? So this is the elementary matrix obtained from I3, right, by subtracting row 1 from row 3 twice. Right? So this is obtained from I3 by row 3 minus 2 row 1. Okay, and now let's just take any old 3 by 3 matrix, A, B, C, D, E, F, G, H, I. And let's multiply and see what we get. First row, first column, A. Right? First row, first 3 columns, you get A, B, C. Right? A plus 0 plus 0, B plus 0 plus 0. Right? So you just get A, B, C. Second row, each column, right? 0 plus D plus G, 0 plus E plus H, 0. 0 plus D plus 0, 0 plus E plus 0, C, 0 plus F plus 0. So it's the same thing. Last one, minus 2A plus 0 plus G. Oops, I'm going to have to make that bigger. A, B, C, D, E, F. So minus 2A plus G. Right. Third row, second column, minus 2B plus 0 plus H. And then third row, third column, minus 2C plus F plus I. Right? So this is the matrix obtained from A, B, C, D, E, F, G, H, I, by that same row operation. Okay? So elementary matrices, they do row operations. They encode the row operation algebraically in, a fairly obvious way. And that's one of the cool things about them. All right. So here's the theorem. An n by n matrix A has an inverse matrix if and only if A row reduces to In. Furthermore, performing the reverse of those performing the reverse of those row operations, no, performing those same row operations taking A to I on the matrix I will take I to A inverse. Okay? So that's the technique. But first let's prove the theorem. Okay? An n by n matrix A has an inverse matrix if and only if A reduces to In. Okay? Proof. So if and only if, there's two directions to the proof. So A has an inverse if and only if A reduces to In. So first assume A has an inverse. First assume A has an inverse matrix. So now, for every B in R n, right, the equation A times X equal to B yields a solution as follows. Right, so you have A times X equal to B. So then A inverse, we're assuming it exists. So let's use it. But this is equal to In. But In times X is just X. Right, so that's the solution. In section, what was it, 1.9? Was it 1.9 or 1.8? I forgot exactly. So in section 1.8 and 1.9, we discussed that AX equal to B has a solution for all B if and only if A has a pivot in every row. Right? But since A is square, it must have a pivot in every column too. Right? So A row reduces to row reduce to, something with the pivot in every row in every column. Well, once you get a pivot in every row and every column, then you can clear out everything and make zeros, right? Which scales to in. So given that you had the inverse, a row reduces to in because this equation always has a solution. So you got to have as many pivots as you need. We'll just pivot in every row. Conversely, okay, assume that a row reduces to in. Thus, there are elementary matrices E1, E2, ET, such that, right, these are the row operations. ET times E2 times E1 times A is equal to I. Right? If A row reduces to I, there are elementary matrices. There's elementary row operations that reduce you to I. But those elementary row operations come in the form of elementary matrices. So there's A inverse. It's just the product of those elementary matrices. ET, E2, E1 is equal to A inverse, right? Because you're multiplying A by this guy and getting the identity. In. That's it. Now what about the furthermore part? Furthermore, okay, you find A inverse, okay, by multiplying the by doing those same row operations to I. Is that the way I said it? Furthermore, performing these same row operations taking A to I on the matrix I will take I to A inverse. Okay, so this is A inverse. For the furthermore part, right, A inverse is equal to ET E2 E1. So A inverse is equal to ET E2 E1 IN. Because the identity matrix is just, when you multiply by the identity matrix, you just get 1, right? Thus, A inverse is obtained from I by these same row operations, right? I can always multiply by the identity matrix on one side because it doesn't change anything. It's the identity matrix, right? So this product is equal to that product just as a product. However, this product also represents taking sequence of elementary row operations from I. And in the end, you get the result, which is A inverse. Pretty neat. It's a real simple characterization of when an inverse matrix exists and how to find it. So for example, we get a reasonable example. So let A equal 1, 0, negative 1/6, 2, 1, 0, and 0, minus 3, 1. Find A inverse if it exists. All right, so what you do is you take this augmented matrix. You put A on one side, and then you put I3 on the other side. And then you reduce to I3. And then on the right, you're going to have A inverse. You just perform row operations simultaneously. Take row operations, reducing A to I3. And then simultaneously, you're doing those row operations to I3, and then that'll give you A inverse on the right. If at some point you don't have enough pivots, then you know there is no inverse. If at some point you find that A doesn't have 3 pivots, then you know that A inverse doesn't exist. Okay, so let's give this one a shot. So here we've got this matrix here, and then you put the identity matrix here. Okay, so I'm going to subtract row 1 from row 2 twice. All right, so 2 minus 1, so we got 1, 0, minus 1/6, 1, 0, 0. 2 minus 2 is 0, 1 minus 0 is 1, 0 plus a third is a third, and then this is going to be minus 2, 1, 0, 0, 0, 1. Last row, just leave it like that. Okay? Next, I'm going to add row 2 to row 3 3 times. Add row 2 to row 3 3 times. So first row and second row don't change. 0, 1, 1/3, minus 2, 1, 0. So subtract it 3 times. Or no, add it 3 times, I'm sorry. 0, 0. So if I add this 3 times, I get 1 plus 1 is 2, right? 3 times 1/3 is 1 plus 1 is 2. And then this is going to get multiplied by 3 and added to that. So that's minus 6, 3, 1. Okay? Next, divide this line, row 3, by a half. 1, 0, minus 1/6, 1, 0, 0. 0, 1, 1/3, minus 2, 1, 0. 0, 0, 1, minus 3, 3 halves, 1 half. Okay? Next, I'm going to subtract row 3 from row 2 1/3 times. And add it to row 1, so I'll do them both at the same time. And then add it to row 1 1/6 times. Okay, so I'm going to multiply this by 1/6 and add it to that. So that gives me 0. Multiply this by 1/6, and I get minus 1 half plus that is a half. Multiply this by 1/6, then I get 3 over 12. So this is 3 over 12, which is 1/4. Multiply this by 1/6, which is 1 over 12. Okay. This row, I'm going to multiply, this row, I'm going to multiply row 3 by 1/3 and subtract it from here. So 0, 1, 0. Multiply by 1/3, get -1. Subtract, I get -1. Multiply by 1/3, I get a half. Subtract, I get a half. Multiply by 1/3, I get a sixth. And subtract, -1/6. And lastly, oh, I'm done. There's a 0 here, so we're done. 0, 0, 1, -3, 3/2, 1/2. So this is A inverse. Okay, let's check. So what was A? Again, A, oops. Come on. There was A right there. And this matrix is 1/2, 1/4, 1/12, -1, 1/2, -1/6, -3, 3/2, 1/2. Okay, first row, first column. A half plus 0 plus a half is 1, right? 1/2 plus 0, and then multiply these two together, you get a half. Next, a quarter plus 0 minus 3/12, which is a quarter. That's 0. 1/12 plus 0 minus 1/12, 0. Second row, 1 minus 1 plus 0, 0. A half plus a half plus 0 is 1. 1/6 minus a sixth plus 0 is 0. 0 plus 3 minus 3, 0. 0 minus 1/6, 0, no, not 1/6. 0 minus 3/2 plus 3/2 is 0. And then 0 minus, no, 0 plus 1/2 plus 1/2 is 1. So that checks out. You actually only have to check one direction. Right? So actually, you don't have to check multiplication in the other direction. Okay, you just have to check it in the one direction, and if it works, then you know that that's the identity. Okay. So it's a it's a pretty simple algorithm. It's a nice characterization of when an inverse matrix exists, and it gives you a nice algorithm. And again, it's just row reductions, right? I mean, like everything we've done in the course so far, it all just boils down to doing a row reduction. Okay? And I guess one other example I could show you, sort of dealing with that, would be something like this. So here's another example of usage. So we did this in that proof, but here's a look at it again in a specific example. Given the equation, so A is that same matrix. given A equal to this, and A inverse equal to this, solve the matrix equation, AX equal to, and let's say, make something that's going to get rid of all the fractions, 12 minus 12, 0. Okay? Well, right, A inverse AX is equal to A inverse 12 minus 12, 0, right? So I3 times X is equal to A inverse 12 minus 12, 0. So X, because the identity times X is just X, is A inverse times 12 minus 12, 0. So, I mean, you already did the row reduction, so there's no need to do it again, because you've got the inverse matrix. So that inverse matrix is this right here. Times 12 minus 12, 0. And what do you get? So we have 6 minus 3. 6 minus 3 is 3. And then minus 12 minus 6. Right, minus 12 minus 6 is minus 18. And then minus 36 minus 18. Is that it? Minus 36 times minus 18. Or minus 18. So what's 36 plus 18? That is 14, 4, 5, 54. Minus 54. Yeah. 18, right. Okay. So there's your answer for X. So once you have that identity matrix, you can, or inverse matrix, you can solve equations of this sort. Okay, that's it for our lecture on this section.